All right, problem 33. We're going to go at this problem with conservation of energy. First thing we have to note is we've got this inclined plane. It's at 37 degrees. We got a spring up here, and we got a mass that we're going to press against the spring. All right, it's a 2 kilogram canister. It's pushed against the spring until the spring is compressed to 0.2 meters and released from rest. All right, so if you think about this, and we're 1 meter up. Okay, if we're 1 meter up, oh, let me start over. All right, the distance that is 1 meter is this one, right? And so if this angle is 37 degrees, that means this height, that height is 30, not 30, that height is 1 meter times the sine, right, of 37 degrees. 1 meter times the sine of 37 degrees is this vertical portion. And when we compress the 0.2 meters on the spring, that means we increase that vertical height by an additional 0.2 meters times the sine of 37 degrees. So let's look at what all this means. What is the speed of the canister at the instant the spring returns to its relaxed length? Okay, we begin this part A by saying what energy is stored, what is the total stored energy. So first, there's gravitational potential energy, which tells us that we have 1.2 meters times sine of 37 degrees, right, of height. This is our height. Height is 1.2 meters times sine of 37 degrees. Our mass is 2 kilograms, and then 9.8 meters per second squared. All right, so this is our total gravitational potential energy when we start the problem. 1.2 times sine of radians of 37. Right? All right, just so that we have that out there, that times 2 times 9.8 gives us 14.2. Right? We've got 14.2 joules of gravitational potential energy. Next, I'm going to write U sub S. All right, how much energy is stored in the spring? Well, let me stick in here UG is mgh is, okay. And for your studying purposes, I'll take these and stick them out front. So we got mgh in the equation. Okay. K, okay. Right? Kx squared. 1/2 kx squared is the potential energy stored in the spring. So in this case, this is 1/2 of 170 newtons per meter times, and x is 0.20 meters squared. All right, that's the linear distance that we moved the spring along its length, 0.2 meters. So we're looking at 1/2 times 170 times 0.2 squared is 3.4 joules. 3.4 joules. So the total stored energy at the beginning of the problem is going to be 17.6 joules. Okay. What is the speed of the canister at the instant the spring returns to its relaxed length? Okay. Now we know the total energy in the system. Total energy in the system is 17.6 joules. So now we want the kinetic energy at the instance of release plus the potential energy at released, when it's released, plus the gravitational potential energy. And at this point, UGR, I'll put it. Okay, at this point, there is no longer any energy stored in the spring. We've gotten all of that energy out of the spring. Okay, and so this is 1/2 mv at the release point squared plus mg and h at the release point equals 17.6 joules. Well, they're asking for the velocity, v at the release point. Right? This is the linear velocity along the plane. H at the release point is 1 times sine of 37 degrees. M and G we know, M we know. Okay, so this is 1/2 times the mass is 2 kilograms times V at the release point squared plus 2 kilograms times 1 meter times 9.8 meters per second squared, right, times 1 meter times the sine of 37 degrees equals 17.6 joules. Okay, let's see what that energy is. So 1 meter times sine of radians of 37 degrees, and that times mass, which is 2 times 9.8, 11.8, right? That's 11.8 newtons. So we've got VR squared equals 17.6 joules per kilogram. That's going to give us meter squared per second squared, right? A joule is a kilogram meter squared per second squared, so a joule per kilogram is a meter squared per second squared, minus 11.8 meters squared per second squared. All right, so we're looking at 17.6 minus 11.8, 5.8 joules, or 5.8 meters squared per second squared, and we just take the square root. V at the point of the release is the square root of 5.8 meters per second equals, it's 2.4 meters per second is the velocity at the point of release. All right, part B. What is the speed of the canister when it reaches the lower end of the incline? Okay, so at the lower end, everything, all right, kinetic energy at the lower end, 1/2 mass times V at the lower end squared. Everything at this point has been converted over into kinetic energy. All the potential energy is converted over. The spring has long since been converted over to kinetic energy. So we're looking for total kinetic energy equal to the total energy we started with at the beginning of the problem. And so this is going to give us VL squared equals 17.6 meters squared per second squared, since that's 1/2 times 2 kilograms, and it gives us VL equals square root, you know, the one that's spelled correctly, square root of 17.6 meters per second. All right, equals square root of 17.6 is 4.019 or 4.20 meters per second. And that's it for this problem, for problem, what was this? Problem 33. All right, on to the next.